So in this lecture, we talk about automorphisms of the disk. And although we're not going to go into the theory of harmonic functions, just briefly mention this in order to understand the intuition possibly behind some of the work, some of the mathematical apparatus that we will try to develop. So imagine that what you have is a disk. And this disk, just imagine a quarter. So this quarter will be coated on the top and on the bottom by some color that is a perfect insulator. So this quarter from its face and from its back, it's insulated against intake and exchange of heat. So this quarter is placed in a special device. So you can see the circumference of this quarter is colored by some sort of orange, blue, and yellow. And this represents this device that is able to take a small portion of the side of the quarter and bring it to any temperature you would like. So there is some continuous function that describes the distribution of the temperature on the periphery of the quarter, on its side. And this boundary temperature is, or boundary heat, whatever you prefer calling it, is measured by this function u. Here it is acting on the boundary. So in other words, you specify this point, and maybe blue means that it's cold. Maybe at this point it's minus 30 degrees. So you will select this point and give you as output minus 30 degrees. Now the problem is giving this information, given that we know the exact distribution of temperature on the boundary, how do we determine that inside of the disk? What's going to be the temperature at each point inside of the disk? So in other words, the idea is how do we extend this boundary function to a function that tells us what's the temperature not only on the boundary but also within the disk. And that's mathematically is set as what is u of alpha for every alpha inside of the disk. Now again, some assumptions that we're making is that the disk is made of uniform material, of the same material and at the same thickness everywhere. And this, I believe, and I hope I'm not wrong here, is it allows us to equate, in some sense, the idea of heat and the idea of temperature, because there would be then scalar multiples of each other. Heat is the energy inside, and temperature is a measurement of that energy. So again, the second assumption I already mentioned, the disk is insulated on its top and on the bottom. So in other words, the only possibility for heat exchange with the environment is through the boundary. And the boundary is maintained at a constant temperature at each location. So for example, where you see this blue curve, that's constant temperature. When it's red, that's constant temperature. So there would be some continuous function that that might still vary on the boundary, but that dictates what's the temperature at each point. And then we wait some duration of time. And after some duration of time, this disk should enter a steady state. In other words, this disk will have a fixed temperature at each of its inner points. So we wait until this boundary is dispersed. So I suppose near this yellow zone, temperature very close to the yellow zone might be somewhat yellow. And as you move farther to the blue zone, it will be somewhat blue. But the disk at each fixed point, the temperature is not changing through time. And that steady state heat equation is given by this differential equation here. And it's equal to 0 when it's no longer dependent on time. So functions that satisfy this differential equation are called harmonic functions. And harmonic functions have a strong link to complex analysis in that on the disk it can be easily shown that every harmonic function is the real part of a holomorphic function on the disk. So for holomorphic functions, what I can do is, let's say, let me try to determine what's the value of the holomorphic map f, whose real part is u, at the center of the disk. So I do the following calculation. By Cauchy's integral formula, I know that f of 0 is equal to 1 over 2 pi I, integral from 0 to 2 pi. And this is just the parameterization of that integral. So it's f of e to the I theta over e to the I theta times I e to the I theta. After performing all the cancellations, I obtain this formula. Now, for those of you that remember from Calc 1, this formula is merely the average value of f on the boundary. Now, all I need to do to figure out the temperature at 0 is take the real part of that integral. So here we have u of 0 is equal to 1 over 2 pi, integral from 0 to 2 pi, u of e to the I theta d theta. In other words, what is it saying? It's saying that if I want to know what's the temperature right in the middle of the disk, all I have to do is take the average of the temperature on the boundary. The point here is going to be equal to the average of the temperature on the boundary. So just a moment ago, we made this calculation that tells us that the temperature at the center of the disk is determined as the average of the temperature on the boundary of the disk. Now let's look at an example to try to understand it in more concrete terms. So suppose that I have the boundary divided into 3 segments of different temperatures. So you have this pink segment comprising 1/4 of the disk, and it is at constant 20 degrees Celsius. We have this yellow segment comprising 1/4 of the boundary of the disk, and its temperature is 100 degrees Celsius. And we have a big cold segment, 1/2 of the boundary of the disk, and it is at temperature minus 10. What is the temperature of the center of this disk? Well, according to what we just determined, it will be simply 1/4 times 20 plus 1/4 times 100 minus 1/2 times 10. And we get that the temperature of the center of the disk is 25 degrees Celsius. So the way it was obtained, again, we had assigned the weight to the boundary that is proportional to the ratio of that segment of the boundary to the total boundary. So the question is, how do we go about determining the temperature for other points? For points alpha that are not equal to 0, but are still in the disk. So suppose that I pick this point alpha, and I want to know its temperature. From basic intuition, you can see this point alpha is rather close to the pink region. So it seems that the pink region is going to influence it somewhat more. So it seems that the weight the weight of temperature that would be assigned to alpha, some sort of new average, is going to somehow be more than just its ratio to the circumference. You see that because when you take alpha and you slide it closer and closer to the pink region, it seems that the pink region is becoming a more and more important factor in determining the temperature. It's going to become almost an absolute factor in determining the temperature of alpha if alpha is extremely close. But no, mind that. How do we just figure out a clear and nice way to figure this temperature of alpha in terms of the distribution? So one nice idea would be if we are able to construct a holomorphic function, a bijective holomorphic function phi, that maps the disk back to itself, and it interchanges the origin with alpha. So what we want, if this is alpha, I want to make alpha through this function the new origin. That's what this function is going to do. It's going to take alpha and make it the new origin, and thereby make it, again, the average of the boundary. So the requirements on this function is, again, that it interchanges 0 and alpha, and that it keeps the boundary at the boundary. It doesn't have to keep each point fixed. It can just stretch it and stretch certain segments, make them longer or shorter. So for example, if alpha is close to the origin, it's close to the pink region, this function phi is probably going to take this pink region and stretch it to be nearly the entire circle. But the other yellow and blue segments will still be represented. It will create a new boundary function. So here is how that function would work. So then we would have that u of alpha is u composed with phi of 0, which is 1 over 2 pi, integral from 0 to 2 pi of u of phi of e to the I theta d theta, which is, again, a new weighted average. So let's try to see where we can find such a function using its properties. So first of all, there are very few complex valued functions that are known to us. And the easiest are polynomials, and the next easiest are rational maps. So we know that if we search among rational functions, they include polynomials. We know that if they are of degree 2 or higher, then they are not injective. So injectivity is failing us. So the only class of functions where we are able to search are going to be the class of linear fractional transformations, or the Mobius maps. So you can see that numerator and denominator have degree 1. So we are searching in the class of Mobius maps, because, again, higher degree functions will not be injective. So now let's try to see what happens. So now, if this is the general Mobius map, if I plug 0, I get b over d. And if I plug 0 according to one of the requirements, I should be getting alpha. 0 is mapped into alpha. And if I take phi of alpha, I will get the ratio a times alpha plus b over c times alpha plus d, and that has to equal to 0. And that implies that alpha is equal to b over a. The numerator must equal to 0, and that would make alpha equal to b over a. And I just made another remark, is that be careful, a is not 0. So you see here I'm dividing by a. Somebody might object that a could possibly be 0, but it's impossible. If a is equal to 0, then in this equation, b will be equal to 0. But both a and b cannot be equal to 0, because then the function phi is just the 0, the null function. And that is unacceptable. So then from here we have two values for alpha. We know that alpha is equal to minus b over a, and alpha is equal to b over d. So we have b over d must equal to minus b over a. The implication is that d is equal to minus a. So if we take the original function phi of z and divide all the coefficients by minus a, this gives us this expression, which is alpha minus z over beta z plus 1. Now let's try to figure out what must be beta. Beta here is, of course, c over minus a. So let's try to figure out what's beta. So we know the last determining factor about this function is that it preserves the boundary. It must map the unit circle back to the unit circle. So if the size of z is equal to 1, then 1 is also the size of phi applied to z. So we take phi of z squared, which is phi of z times its conjugate, and we get this expression. Now this expression translates to this important equation 1. We have that alpha squared minus 2 real part alpha bar z plus 1 is equal to modulus beta squared plus 2 real part of beta times z plus 1, where z is, of course, assumed to be of magnitude 1. Letting z equal 1 and letting z equal to minus 1 in this equation gives us those two equations. So we have modulus of alpha squared minus 2 real part of alpha conjugate plus 1 is equal to modulus of beta squared plus 2 real part beta plus 1, and a similar equation below it. So if I take those two equations, I take the top and subtract the bottom and do some very basic arithmetic, I obtain the equation that minus the real part of alpha conjugate is the real part of beta. And if I take those two equations and I add them, I obtain that modulus alpha squared plus 1 is equal to modulus beta squared plus 1. And that implies that modulus alpha is the same as modulus beta. They are of the same magnitude. Now, if I am going to play with equation 1, but this time I'm plugging the numbers I and minus I, which again, they have size 1, then I obtain the following equations. So those two equations that you can see on the board. Now, doing similar arithmetic with those two equations, I obtain that minus imaginary part of alpha conjugate is the imaginary part of beta. So since the imaginary part of beta is minus the imaginary part of alpha conjugate, and the real part of beta is minus the real part of alpha conjugate, we conclude that beta is equal to minus alpha. What's the consequence? We have at last determined the desired function. So this is simply phi of z equal to alpha minus z divided by 1 minus alpha bar z. We are going to see the consequences, and this has a lot of consequences. Very useful function with very useful properties. But before we can begin describing those properties, we need a few results. So this is a very important result called Schwarz Lemma. And Schwarz Lemma tells us that if I have a holomorphic map from the disk to the disk, and f of 0 is equal to 0, then the following will be true. F of z, its modulus will always be smaller than the modulus of z. And the second condition, if at some point z naught not equal to 0, f of z is equal to the modulus of f of z is equal to the modulus of z, then we have that f is a rotation. Third consequence is about the derivative, is that the derivative of f at the origin is always no bigger than 1. And if equality holds, then again we have a rotation. So let's see how this result is proved. So first of all, we made the assumption that f is 0 at the origin, which means that when I give f its power series expansion, it begins with a1z, then a2z squared, etc. The constant term is missing because it's equal to 0. Now this power series expansion gives us the ability to divide f of z by z and still have a holomorphic map. In other words, g of z, which is f of z over z, it has a removable singularity at z equal to 0. So then if modulus of z is equal to r, where r is smaller than 1, we know that since the modulus of f of z by the maximum modulus theorem, it cannot exceed 1. Actually, we don't even need even that. F is mapping into the D. So its image size is no more than 1. We have that the magnitude of g is equal to the magnitude of f over z, which is less than or equal to 1 over r. F of z is smaller than 1, and z is equal to r. And here we apply the maximum modulus principle. So this is not only true on the circle z equal to r, it's true on the inside of this circle z equal to r. Because this function is holomorphic, it takes its modulus can only take its maximum on the boundary, or else the function is constant. So then we can create bigger and bigger circles by pushing r to -1. And we conclude that f of z over z is always less than 1 for all z. And that is just equal, that's very quickly translatable to modulus f of z less than or equal modulus z. And that takes care of I. Now let's see what happens when you have equality. If f of z0 has a modulus equal to z0, then it follows that f of z0 over z0, its modulus is equal to 1. Which means that f of z over z is maximal in the interior of origin. And by maximal modulus theorem, that forces the function to be constant. So f of z over z is constant. And of course, this constant, its magnitude, is equal to 1. So if a constant has magnitude equal to 1, it can be represented as e to the I theta. And what we have is that f of z over z is equal to e to the I theta, or that f of z is equal to e to the I theta times z. And that is just purely a rotation. Now let's look at what happens if the derivative of f at 0 is, what's the situation with it? So first of all, the modulus of f prime of z 0 is the limit as z goes to 0 of the modulus f of z over z. That's the definition of the derivative. Now we know that f of z over z by result I is smaller than 1. So that tells us that the derivative has modulus no bigger than 1. If it happens that the derivative at 0 has modulus 1, we conclude that the function g of z, which is f of z over z, it takes its maximum value at 0. Because g of 0, modulus of g of 0 is the same as modulus f prime of 0, which is 1. Which makes g of z identically, modulus of g of z identically equal to 1 throughout the region. That is to say that g of z is a constant, which means that g of z is equal to e to the I theta, and that readily translates to f of z being equal to e to the I theta times z. So that proves the last result. So now that we have shown Schwarz Lemma, I'm going to try to illustrate several examples, and there are plenty of others where the function that we just defined, this Mobius map phi, and the Schwarz Lemma together give lots of powerful results. So before that, let's just look at the properties of this function phi. So first of all, phi sub alpha is its own inverse. In other words, if I take this function and feed it to itself, I get the identity. Easy to verify. Second property is that the general derivative of this function at alpha is modulus alpha squared minus 1 over 1 minus alpha conjugate z squared. Third property is that if I take the derivative and I plug in alpha, what I will get is minus 1 over 1 minus modulus alpha squared. And that's going to be important in the example I'm going to illustrate here. So first example is, suppose we have a generic function f from d to d. We don't know what it does to the origin. And we want to estimate what could be the size of the derivative f prime of z. So we go as follows. So first of all, we fix z equal to alpha. So we're going to estimate what's f prime of alpha. Now f, we don't know if f maps 0 to 0, so we can directly apply Schwarz Lemma. But if I create a function g, which is the composition of, I take f and I feed it phi of alpha. What's the result? The result is that if I plug 0, I get here, this part gives me f of alpha. Now, f of alpha does not necessarily equal 0, so I compose it with phi or sub f of alpha. So altogether, if I feed 0, 0 will come out. So this function g, since f is mapping the disk to the disk, and since phi of alpha and phi of f of alpha are mapping the disk back to itself, the composition is going to map the disk back to itself. And we have that g of 0 again is equal to 0, so Schwarz Lemma can be applied. So let's first calculate what's the derivative at 0 of g. So the derivative of g at 0 is just a basic chain rule. It's a chain rule consisting of 3 composites. And what we end up getting is phi prime f of alpha at f of alpha, which we can apply the third result, times f prime of alpha, the quantity we really want to estimate, times phi prime of alpha at 0. So by property 3 of those functions, the leftmost expression is just minus 1 over 1 minus modulus f of alpha squared. The middle term is just f prime of alpha, and the last term is modulus alpha squared minus 1. So then, multiplying and bringing it all to one side, we have 1 minus modulus alpha squared over 1 minus modulus f of alpha squared times f prime of alpha is equal to g prime of 0. Now, by Schwarz Lemma, what do I know? I know that the modulus g prime of 0 must be smaller than or equal to 1. Now, the modulus of g prime of 0 is the modulus of this quantity. Now, notice that since alpha is in the disk, numerator is a real positive number and denominator is a real and positive number. So the modulus is simply 1 minus alpha squared over 1 minus f of alpha squared times the modulus f prime alpha. Now, taking this and multiplying across the inequality, I see that 1 minus modulus f of alpha squared divided by 1 minus modulus alpha squared is bigger than or equal to the derivative at alpha. And since, of course, this is true for alpha, we have this estimate. 1 minus modulus f of z squared over 1 minus modulus of z squared is bigger than or equal to f prime of z. So let's illustrate how this estimate in example 1 can be used to determine certain existent properties of functions on the disk. So here is a typical question. Does there exist a function from the disk back to itself with the following conditions? The function f of 1/2 is equal to 3/4, and f prime of 1/2 is equal to 2/3. So we begin by this estimate. So this estimate that we have right over here. We have some relationship between the function at z and its derivative at z. So we calculate 1 minus modulus f of 1/2 squared over 1 minus modulus 1/2 squared, and that will give us the number 7 over 12. Now 7 over 12 is smaller than 8 over 12, which equals to 2/3. And 2/3 happen to equal the modulus of the derivative at 1/2. Now notice what happened here. This number should be at least as large, no smaller than the derivative. So since the derivative is bigger than this number, there is no such holomorphic function. So no holomorphic function satisfying the properties that I listed here exist. So here is one other illustration of the combination of this function, of this Mobius map, with Schwarz Lemma. So again, suppose that we have a map that is non-constant and is mapping the disk into the disk. That's just another way of saying it. So then this holomorphic map satisfies the following inequality. Now, how do you arrive at such an inequality? So to apply Schwarz Lemma, you would have liked the function to be equal to 0 at 0. So you can achieve that as follows. You can create a new function g, which is the composition of f with phi of f of 0. So look, if you plug 0 into f, you get f of 0, and then apply this map to it. It maps f of 0 to 0. So then g satisfies g of 0 equal to 0, and Schwarz Lemma applies. So Schwarz Lemma tells us that the magnitude of g of z is less than or equal to the magnitude of z, with equality holding if and only if g is a rotation. Hence, we have that magnitude of z is bigger than this quantity. That's just evaluating the composition of functions. Now, I can create a smaller quantity than this by appropriately expanding the absolute value. So here, I consider the difference of the absolute values, which is smaller than the absolute value of the difference. And on the bottom, I divide by a larger number. So then we have that magnitude of z is then necessarily bigger than this quantity. Now this quantity then implies that if we just multiply the denominator by magnitude of z, we get this part, and this part is clearly positive, is bigger than this part. So then rearranging and keeping inequalities, we arrive at magnitude of f of z is bigger than or equal to magnitude f of 0 minus magnitude of z divided by 1 plus magnitude f of z times magnitude of z. So this is a very quick derivation once you realize that Schwarz lemma is applied. Now this proves this part of the inequality. The other part of the inequality is established in a similar fashion, so try it yourself.